Jeff Brock from Brown University, and he's going to be speaking on uniform models and bounded geometry.
Okay, well, I'd like to thank the organizers. Particularly the local ones. After all of my collaborators were mysteriously unable to attend the conference, that left one man standing to give the talk. So what I'm going to talk about is joint work with Minsky, Namazi, and Souto. Sort of a ongoing project to understand the geometry of closed hyperbolic three-manifolds in terms of combinatorics coming from their topological description. And the idea here, just to give some history, is to the idea is to sort of explore the interplay between flexibility and rigidity in hyperbolic geometry. Flexibility being more what one thinks of as the study of Kleinian groups. So the study of the deformation theory of infinite volume Kleinian groups in terms of Teichmuller theory, and more recently in terms of combinatorial invariance associated to surfaces, such as the curve complex, the Pants complex, et cetera, and the internal geometry of the infinite volume hyperbolic three-manifolds. And then turn that back to the question of rigidity. So the fact that after the work of Perlman and Mostow, really, one should say Perlman-Thurston here, that once one knows certain topological restrictions on M, so that M is closed, irreducible, and a toroidal with infinite pi 1, then M can be realized as the quotient of H3 via a discrete subgroup of the isometries of hyperbolic 3 space, and gamma is unique up to conjugacy in PSL2C in the isometries of hyperbolic 3 space. So I should say that the study of the connections between the topology of M and this geometric structure, a hyperbolic structure on M, it certainly is not new. So questions such as, which have a rich history in the field, such as, what's the volume of a hyperbolic knot? Or how does one relate volumes of knots to crossing number, or twist diagrams, other things like this goes really back to the beginning of the original existence theorems, seeing it as a new invariant. So what I sort of want to focus on, though, is to play off of the connection to the Kleinian group theory that comes out of the Alfors-Bears study of deformations of Kleinian groups. And let's just focus in on a specific case that was mentioned in Steve's talk of the existence of a parametrization by a product of Teichmuller spaces, which trying to write large because I find it difficult to see back there, but to the quasi-Fuchsian hyperbolic three-manifolds. So this is a homeomorphism from a product. You choose a surface X and a surface Y, and you get a unique quasi-Fuchsian hyperbolic three-manifold, which is realized as the quotient of H3 here in the ball model via a single surface group. So gamma is isomorphic to pi1 of S. So here S is a closed hyperbolic surface for the sake of argument. And the quotient of, there's an invariant Jordan curve, the limit set of the group. And the quotient, so we'll call this lambda of gamma, though I don't think it will come up again. And the quotient of all of this by gamma, these two domains, is the pair of Riemann surfaces X and Y. Okay, so this comes out of an analytic solution to the d-bar equation. So it's kind of a black box in terms of the geometric story. So you feed in these two Riemann surfaces, and out comes this quasi-Fuchsian group. Nevertheless, there's a great deal of geometry going on inside this manifold, and that's what I think it's fair to say Thurston sought to exploit to understand the question of how to put geometric structures on closed hyperbolic manifolds. Okay, so in particular, to study the case of three manifolds that fiber over the circle, which I'll say more about in a moment, Thurston studied what would happen if we let these surfaces drift off to infinity in Teichmuller space. Okay, so if we have an instance where x and t and y sub t are diverging in sort of different enough directions in some sense that can be made precise, the sequence of Kleinian groups actually converges both in the sense of representations of pi1 of S to PSL2C and in the Gromov-Hausdorff topology. Okay, so let's just say as a heuristic, if we let x sub t and y sub t wander off to these laminations, these are naturally in the Thurston boundary initially. One can forget the measure, one discovers after studying these things for a while. These are initially measured laminations in the boundary of Teichmuller space. Okay, and under certain conditions on nu minus and nu plus, this sequence converges to a limit q infinity. Okay, so in particular, so this q infinity bears some relation in a certain kind of iterative example using pseudo-Anosov monodromy to the three manifold that fibers over the circle. But then he became interested in its own right in the question of what parametrizes such limits. So in fact, can these invariants be used to parameterize limits? Do they depend on anything else? Is there more than one way to approach? Can you get different limits by approaching these laminations in different ways? Okay, so that is a special case of the ending lamination conjecture. And just to put all this in context, let me say it's a meta question. Can we understand geometry of, say, q infinity in terms of these combinatorial pieces of information? Okay, so you might say, well, what's combinatorial about these things? Well, it turns out they have combinatorial properties just as closed subsets of the surface. The way they wander around the surface has certain combinatorial structure to it that one can tease out. And well, what he was really interested in was this question I said just a second ago. The ending lamination conjecture was, for example, do nu minus and nu plus determine Q infinity uniquely? Okay, and that is now known, but it came about through sort of an exhaustive description of the geometry. Okay, so this is a theorem. This is really Minsky's program, followed up by work with myself and Canary. Let me be more proper here. Which says more, namely that given the combinatorial information, there is a combinatorial model three-manifold M nu plus minus, let's say, and an L by Lipschitz diffeomorphism to this Q infinity where L depends only on the surface, the topology of the surface. Okay, and this, as it turns out, works for more general instances. One need not assume that Q is a limit of the quasi-Fuchsian manifolds, although that turns out to be true. So let me distinguish this by writing M nu plus and then blackboard M for the model. Okay, so what does this have to do with the question of determining Q infinity uniquely? It doesn't look very unique. It's just L by Lipschitz. Okay, and that's where the rigidity plays a role. Okay, so there's another form of rigidity due to Dennis Sullivan. And that allows us to promote this to more information. So if we have, say, a putative pair of hyperbolic manifolds with the same combinatorial data at infinity, the model theorem tells us they are L by Lipschitz to a common model. Okay, so say phi, or F, I guess, and F prime, which allows us to construct a bi-Lipschitz diffeomorphism between the two hyperbolic manifolds. And by Sullivan's rigidity theorem, that's homotopic to an isometry. Okay, so this is just one example where having sort of somewhat floppy or coarse information about a manifold yields an on-the-nose sort of rigid result. Okay, so in particular, it's sort of the philosophy behind Mostow, Sullivan, and this general picture that obtaining information that is coarse in some sense or other, or up to by Lipschitz, can nevertheless be powerful toward understanding finer geometric invariants. Okay, so there are various terms floating around now for this. One is sort of quantitative topology. So we can say we're quants. Okay, so this is, again, just more general philosophy. If you start with topological data, such as way to construct a three-manifold, like a knot or a fibering over the circle or a Heegaard splitting. The question is, how do you get from that geometric info? Okay. So, and the way I want to suggest is, we've seen some examples of this already, but that using the machine that produces this bi-Lipschitz model or variants thereof is a good way to get at some of this information. So that's what I'm going to talk about today. In particular, we'll focus in on what exactly guarantees, and this was actually Minsky's first result in this direction in the case when we have a manifold homotopy equivalent to a surface. What is enough to guarantee? So what guarantees a lower bound to the injectivity radius? Okay. So this is sometimes called bounded geometry for us, although I know in other schools that requires more. But for the purposes of this talk, that's what I'll mean. Or if there were parabolic elements, sometimes what you mean is the lower bound to the length of the shortest closed geodesic. And those two things behave qualitatively similarly. Okay. So again, this case of the mapping torus psi modulo x cross 0 is identified to psi of x 1. So Thurston showed this is hyperbolic. Oops. If and only if psi satisfies this pseudo-Anosov property. Okay, which is essentially that it creates no obstructions to hyperbolicity. It introduces no essential tori in the fibered manifold. Well, to read off the story in the context of the fibered case, the idea here is if you have a fibered manifold, sort of caricatured like this, it has a fiber, say. It also has an infinite cyclic cover. And if we take, which is translationally invariant by an isometry that acts in the homotopy class of psi. Okay. And how does this relate to the ending lamination story? Well, if I fix a curve, a simple closed curve in the surface, and look at its geodesic representative in the manifold, I can take forward and backward iterates of this. These converge to, say, lambda minus and lambda plus. And it was kind of the double limit theorem, first of Thurston, guaranteed that this, just like the original sequence of quasi-Fuchsian manifolds, that this sequence converges, although he considered, sorry, to be precise, he considered what one gets by taking a double limit of quasi-Fuchsian groups, by letting psi act as automorphisms of Teichmuller space. And then, in this case, this converges to a manifold M lambda plus minus with these as so-called ending laminations. Okay, so where is this heading? Well, so any such manifold has some lower bound on its injectivity radius, right? It's closed. So it's just compactness. But let's say you wanted an a priori lower bound independently of the manifold in terms of these laminations. Okay, so maybe you have some family of manifolds and they exhibit some similar property, which is that they're all of bounded geometry. So what the model, and this was originally Minsky's bounded geometry theorem, the model gives you criteria for this in terms of combinatorial invariance of the lamination. So I'm going to try to describe those, and this is always a bit of a morass, so what I'm going to do is to just stick to first the SL2Z case. Okay, so SL2Z, of course, acts on the upper half plane. And the upper half plane is, of course, always drawn like this. And that usually gets a laugh, sorry. And we can take a triangulation called the Ferry tessellation, okay, that lands at the rationals, all of them, 0, infinity, 1, minus 1, etc. That has the property that two rationals are joined by an edge if PQRS as a matrix has determinant 1, okay? Or one way to say that is if they're the image of the imaginary axis under an element of SL2Z, acting by isometries. Now, well, if you've thought at all about the modular surface or done any Teichmuller theory, it may not come as such a surprise to you that there's a condition in terms of the irrational endpoints of a geodesic that lands at irrational endpoints. There's a condition that guarantees that the projection of that geodesic to the modular surface stays in a compact subset. Okay, so I take some geodesic. Let's say I have suggestively lambda minus and lambda plus endpoints on the circle at infinity that are irrational. Well, so what's the condition? Well, there's a way to write this as a, it gets sort of hard to draw beyond the first couple of triangles, but something called the pivot sequence. So we can redraw the itinerary of this purple geodesic as it goes through the Ferry graph. It cuts through some number of triangles on one side, and then it switches or pivots. Okay, so over here it's cutting off triangles to the left, and here to the right, and so forth. And if we count the number of triangles, that yields up to appropriate conjugacies the continued fraction expansion of the endpoint. Okay? So number of triangles in a pivot, or kth pivot, is the kth entry in continued fraction expansion. Okay, so there's sort of a bi-infinite continued fraction expansion here. And bounding these, so bounds on the entries corresponds to bounded projection, or co-bounded, if you like, to H modulo SL2C. Okay, and there's a literal sense in which it corresponds to bounded geometry in the sense of hyperbolic manifolds as well. So if I take my limiting sequence now in the type S11 cross type S11, where S11 is the punctured torus, which happens to be the upper half plane. I mean, the Teichmuller space is the upper half plane. Well, a geodesic like this gives me a sequence of points in Teichmuller space limiting to lambda plus and lambda minus at infinity, which in turn gives me a sequence of quasi-Fuchsian groups xn, yn in the space of quasi-Fuchsian groups, or punctured torus groups. Okay? So here the condition that one wants when you have a boundary curve is that this should be held parabolic, okay? And indeed, if these surfaces converge to these irrationals, lambda minus and lambda plus, with bounded continued fraction entries, then the limit has bounded geometry. Okay, so bounded geometry for this purple geodesic on the modular surface corresponds to bounded geometry for the quotient hyperbolic 3 manifolds in such a limit. All right, so the thing about math talks is they're actually sort of exponential in complexity as you go. So we're going to make the jump to hyperspace. So what do we do in higher genus? So what plays the role of the continued fraction entries? Well, the idea is that if we have S of complexity higher than the punctured torus, let's just say, again, going back to S closed, G greater than or equal to 2, we can consider something called the curve complex. Note that here, these, in addition to being rational numbers, these points that are rational are describing simple closed curves on the punctured torus. Okay? So in some sense, this graph is encoding information about the simple closed curves on the punctured torus. So in the higher genus case, we have vertices are in this set S of simple closed curves. So they're in one-to-one correspondence. And then edges, or k-simplices, correspond to configurations of pairwise disjoint configurations of k plus 1, pairwise disjoint curves. Okay, take those vertices, and then you can stick a k-simplex in there. Well, this complex possesses a great deal of geometry. In particular, as a metric space with just the standard Euclidean metric on each simplex, the curve complex is hyperbolic in the coarse sense. Okay, that's due to Minsky. And the boundary is naturally the ending lamination space, or the space of potential filling ending laminations on the surface. So let's just say these are the points that we are interested in considering as limits of our families of surfaces here. And just as, in some sense, the continued fraction expansion, the kth entry tells you how different the endpoints are relative to some particular rational. We consider here, so given, let's start with perhaps a pair of maximal simplices. Maximal simplices. So these are Pants decompositions. We consider a pair. We can measure with respect to any subsurface of S. We can measure the distance of projections, and they literally are almost nearest point projections of these simplices to the link of the simplex corresponding to the boundary of Y. Okay, so the boundary of a subsurface Y gives you some simplex in the curve complex. You consider the nearest point projections to the link, and then we measure the distance. Okay, and these play the role of the continued fraction entries. There's a lot that can be said about these things when they're large, but what we're going to do is bound them all, okay? So maybe I won't say that much more. Okay, so we use these projection distances, so-called, to define the notion of bounded combinatorics. Okay, so we say, this is due to Minsky's idea, that a pair of simplices, maximal simplices, u minus nu plus, or delta minus delta plus, have R bounded combinatorics if, for all proper subsurfaces y of S, these distances dy delta minus delta plus are bounded by R. Okay, so there's a couple of disclaimers that have to be made. First of all, there's some special cases for the definition of the curve complex when y has low complexity, like a punctured torus or a four-hole sphere, in which case it's just this graph that I erased a moment ago called the fairy graph. So try not to worry too much about that. And moreover, one really wants to consider maximal simplices with some additional transverse data. These are called markings. Imagine you're picking a family of curves complicated enough on the surface that if you bound all of their lengths, then that constrains the geometry of the surface to a compact set. That's really all one needs. Okay, and then one can measure these distances. I should just say that this isn't so complicated. There's a surgery procedure that realizes this notion of a projection. So if I have a curve passing through a subsurface, green is always an unfortunate color, the green blackboard. Okay, then there's a way to realize the image of a projection to the curve complex of the subsurface just by taking a regular neighborhood of the curve union the boundary and then taking its boundary. That gives you some collection of curves. And after futzing around with resolving intersections and whatnot, you get some notion of a simplex in the curve complex of the subsurface. Okay? Now, the idea is that this is enough to guarantee, in the same way it did in the punctured torus, bounded geometry. Okay, so if we, in fact, there's a limiting notion as you tend out to the boundary of the curve complex. You can send these markings out to the boundary of the curve complex, and they give you the projections are still make sense. So if we replace these, say, by these laminations, nu minus and nu plus, we can still measure the projections. And then Minsky's theorem is that m nu minus nu plus minus has bounded geometry if and only if, in some appropriately quantified sense, nu plus minus has bounded combinatorics. Okay, for those of you who like quantifiers, specifying an epsilon gives you a bound for the combinatorics such that the manifold will have epsilon bounded geometry, and specifying a bound on the combinatorics gives you an epsilon. Okay? They need not be correlated beyond that. Okay, so good. Note that this is a first step towards translating information from this technology back to the setting of closed manifolds, because right away one can say in the case where we had a pseudo-Anosov double limit that the bound on the injectivity radius only depends on these limit laminations. Okay? It doesn't depend on anything about how we got there or compactness or anything like that. So that means a statement about infinite volume manifolds is translated back into a statement about closed manifolds. So the fibered 3-manifold mapping torus M sub psi has epsilon sub r bounded geometry if the laminations, which of course depend only on the monodromy, have R bounded combinatorics. Okay, good. So we're still sort of in relatively ancient history here. So let's see if we can get up to date. So another construction of a combinatorial construction of a 3-manifold is the notion of a Heegaard splitting, which we've heard some about. And there's been some exciting recent work on minimal surfaces coming from Heegaard splittings that's actually going to be important in facilitating the completion of this project. And there's a young man in the audience who I owe a few beers for this. So a Heegaard splitting, of course, we take the union over the boundary surface of two handle bodies. Okay, and let's just assume that we start with a standard genus G splitting, so boundary H sub I is homeomorphic to S sub G, and we start with the standard genus G splitting of S3, and then we can find others by taking an element psi in the mapping class group of S sub G and precomposing it. So this will be H1 union psi. Well, I said pre-compose, it doesn't really matter. Psi H2, okay? So if we choose new ways of gluing the Heegaards splitting together, we get these different splittings. Depends only on the isotopy class of psi. Okay, so there was an initial result in this direction, which is due to Hossein Namazi. Which said that if we take psi chosen properly, so if delta, let's just take one of these markings, delta psi delta has R-bounded combinatorics in the sense described, then we need one more condition, and the distance in the surface S between delta hat and psi delta hat is sufficiently large then HS psi has epsilon sub r bounded geometry. Okay, and in fact, and you may be noticing some things here, the cognoscenti. So indeed, all one needs by Perlman to guarantee that the manifold is hyperbolic is that this condition is that this distance, sometimes called the Hempel distance, or roughly the Hempel distance should be at least 3. Okay? So, but I haven't been too specific about where these things come from, so let's not worry about that. So, and then the combinatorics give you a way to, again, start from the Kleinian group setting and build up what should be a geometric model for this family of Heegaard splittings, where the distance is large and the combinatorics are bounded. And so that's exactly what he did. But he proves more, which is that in this setting, there is also a model. Okay, and it's kind of curious what the model looks like. You might have a guess. So in fact, we've seen examples of 3-manifolded fiber over the circle. They have this periodic cyclic cover. Well, in fact, one can just take the 3-manifolded fibers over the circle with monodromy psi and take a fundamental domain for that, and then cap it off with bounded diameter handle bodies, and that gives a model for what the manifold, this Heegaard splitting, will look like. Okay, so what do I mean by all this? So the fundamental domain should just look like an interval bundle over the surface. And Namazi's model gives a bi-Lipschitz diffeomorphism from a copy of this fundamental domain together with 2 bounded diameter handle bodies. When I say bounded, I mean bounded only in terms of the topology of the splitting, in terms of the Heegaard surface. And then some fundamental domain, which we can call B sub psi here. Okay, and this whole thing has bounded geometry. So this, well, it's fair to say this got us all thinking when he proved this. I should also mention that somewhere, this was in his thesis, and somehow in the intervening period, there was actually a paper that came out that investigated the case of an arbitrary pseudo-Nassau. So this is Namazi Souto. I can't write today for some reason. Proved the model theorem for the Heegaard splittings corresponding to an iteration psi to the n, and then proved the theorem for n sufficiently large, okay, which is a little different than what I did. I just assumed that the distance in the curve complex between the 2 markings was large. Okay? So let's see. So what this leads to is actually a very general, almost too general for a talk, theorem in terms of gluings with bounded combinatorics. Okay, so I'll stop writing for a second and just say what the rough idea is. So imagine someone gave you a Tinker Toy set or something, just a box that has a certain list of objects that you can play with, and you have ways to stick them together. So I spent a lot of time doing this when I was a child. And the objects are, instead of Tinker Toys, compact, atoroidal, irreducible 3-manifolds. Okay, so they're hyperbolizable 3-manifolds. They can have compressible boundary, make no assumptions on that, or acylindrical parts and all kinds of strange things. And then you just have a finite list of those, okay? And now you're allowed to pair up boundary components by gluing maps. And you only make one requirement, which is, well, you make a couple of requirements. So the first requirement is that the gluing maps in the curve complex of the associated surface for the gluing map should have definite separation. Now, that doesn't mean anything because I haven't given you any curves yet. But they're naturally associated curves to this list of Tinker Toy blocks that I've been given. So there's sort of what are called decorated manifolds. They're manifolds that come with some boundary data, some marking, delta on the boundary, okay? So you have a list of manifolds with marked boundary. Now you want the gluing maps to separate the markings on the boundary. And then you want the gluing maps also to have bounded combinatorics in the sense of that we've given. Okay, now the conclusion is that once they have definite separation and bounded combinatorics, then there is a model, and that model is by Lipschitz to a hyperbolic metric on this gluing, and the model has a lower bound to the injectivity radius in terms of the combinatorics and the pieces in the Tinker-Toy set. Okay, so that's the statement of the theorem in sort of childhood language, but the one notable thing that doesn't come out the first time you hear it is that you're allowed to take from this finite list infinitely many pieces and glue them together. And as long as you satisfy these conditions, there will be some hyperbolic metric. There is a hyperbolic metric. And in fact, it's rigid by a theorem of McMullen. Okay, so it's a sort of new hyperbolization theorem for three manifolds with infinitely generated fundamental group. Now, I had a feeling that the thrust of that would get lost in the following statement of the theorem, so I hope that was helpful. So we have M is a finite collection of atoroidal three manifolds with a marking on each boundary component. Okay. Then we have, for all r greater than 0, there exists d, k, and epsilon, so that an M gluing, okay, and this M gluing is going to be just pairing up of some of the pieces in the set M of three manifolds. An M gluing X, call it X, with R-bounded combinatorics and heights. So these are the distances in the curve complexes for the gluings. Heights at least D is hyperbolic, and K by Lipschitz to a model M sub X. Okay, so there's a model map F sub X from a combinatorial model to the hyperbolic metric on this manifold. It's K by Lipschitz, and the injectivity radius in this metric is at least epsilon. Okay, so what is the model? Well, you can sort of tease it out from this picture. Essentially, these would play the role, these handle bodies would play the role of the compact atoroidal three manifolds, and then the gluing is pairing up boundary components with appropriately large, in terms of this constant D, distance in that curve complex and satisfying this bounded combinatorics condition. Now, like I said, there's some things to unpack here. In particular, what does this R-bounded combinatorics condition mean? I've only given you a list of manifolds. So I need to say more here. This is what's called a decorated manifold. Okay, and these manifolds come equipped with some boundary data, some collection of curves that are supposed to bear some relation to their internal topology. Okay, so So that's the statement, and the proof involves kind of an interesting sequence of arguments, many of which are inspired by Hossein's original thesis. But I thought maybe it would make sense, well, maybe I can just say a couple of the steps. So first, do I want to do this? 5 minutes left. Let me just get to the Heegaard case, since that was what I advertised I would say, and then hopefully I can say a bit about where the meat is. Okay, so in the setting of Heegaard splittings, so more concretely, this all seems a little abstract. So so we have the following in terms of, so this relates, in fact, the first case that I'm going to state here is a direct consequence of this theorem, that Heegaard splittings that come from R-bounded combinatorics have bounded geometry. Okay, so given G, and a genus G, bound R, there exists epsilon so that all but finitely many closed 3 manifolds with a genus G Heegaard splitting and then the appropriate notion of bounded combinatorics, which is here R-bounded compressions. It's more general than Namazi's case in that it allows for certain compressions to take place near the handle body, and it allows for the structure to continue to develop. Okay, so has injectivity radius at least epsilon. Okay, and then maybe what I'll focus in the last few minutes on is a converse, which is sort of illustrative of what's going on. So conversely, given G, again, and epsilon, there is an R so that all but finitely many closed hyperbolic 3 manifolds with a genus G splitting and injectivity radius at least epsilon have R-bounded compressions. Okay, so let me just give you an idea of why this second statement is true, and it sort of illustrates what the combinatorial picture should be. Okay, and in fact, what I'm going to do to start out is discuss what happens when we're simply given M, a complete hyperbolic structure, M homeomorphic to the interior of a handle body. Okay? So, and now I want to assume the injectivity radius is at least epsilon. And what our bounded compressions should be should present themselves. Okay, so here's the idea. So what is a sort of rough picture of what this looks like. We have some handle body. It has a convex core boundary. Call it, say, X. And maybe I'll leave this vague for a minute, what happens down here. And then we make the following claim. Okay, so X, this is sort of a singular surface, but there's a close by embedded surface. So we can work with that one. It's metrically similar to X. And we make the claim that if the length of the shortest meridian, let's call this X prime, on X prime is at least R, let's say L, then there is a K by Lipschitz, a standard product region, so a K by Lipschitz embedded S cross 0, 1 with S cross 0 mapping to diffeomorphically to X prime. So here's the idea. I look at the length of the shortest meridian. If that's bounded below by some number, I can find a product region in my manifold. So what's the argument? Well, I assume, so I don't have any quantifiers again, so there exists L, and then this K is in terms of the genus, okay? So, so what I do is I say assume not, and I take a Gromov-Hausdorff limit. So I assume that I have some sequence of manifolds just like this, Mn, where the length of the shortest meridian is tending to infinity. Okay, then there's actually some interesting technology that goes into analyzing what the limit can look like. Okay, so we have, what we claim is that if the length of the shortest meridian is getting longer and longer, then we can take some limit in a space of representations of pi1 of the boundary surface X into PSL2C. Okay, so this may look funny to you because, in fact, this is not in the space of handle body groups. These are non-faithful representations because X is the boundary of a handle body. Okay? But if the length of the shortest meridian is tending to infinity, these are what are called eventually injective representations. So the shortest word in the kernel is growing without bound. So with this assumption, rho n tends to a faithful limit that is 1 to 1. And we have a pretty good understanding of what these faithful limits look like. I should say that to show that the geometric limit is even finitely generated is not trivial. Okay, so that's a theorem. So there's also a geometric limit, m sub g. So m sub g has finitely generated fundamental group and is therefore tame. That's due to Berenger and Souto. Okay, and these laminations and the convex core has infinite volume. So the injectivity radius is bounded above in the end. So in fact, the limit looks like a degenerate end. And when you have a degenerate end, geometric convergence provides a product region for you. You can just map it back from the geometric limit. And then the construction is inductive. You can continue to find these product regions until the length of the shortest meridian is bounded. And when that happens, you insert a 2 handle, a disk along the boundary, and the process starts over with 2 new. So you get a compression body now with interior boundary, where this is now the exterior boundary. And it continues until you run out of possible compressions. So this is the picture that Chaim was alluding to in his talk, again, with the assumption that the injectivity radius is bounded below. Okay, well, I'm out of time, but I just wanted to remark that in the Heegaard splitting case, one of the key steps is in the setting of the strongly irreducible Heegaard splittings, which is where one assumes that meridians from either side of the Heegaard splitting intersect, and the thing is irreducible in the first place. And then the Pitts-Rubinstein theory, fleshed out by Daniel, gives this minimal surface, which allows you to take the same geometric limit process. So theorem of Mark-Lackenby tells you there's a bounded diameter, that this minimal surface has bounded diameter once you know the genus is bounded. And so that allows you to take a geometric limit in this same sense. And you sort of expand the Heegaard splitting in either direction with this minimal surface as your anchor point. So those developments will sort of facilitate wrapping this all up. Okay, sorry for going over. Thanks.
Questions for Jeff? Yeah.
No, no. So the combinatorial condition is what's forcing the lower bounds on the injectivity radius. And in fact, the same kind of construction that Joel was talking about in his talk, where you take in these gluing maps for the Heegaard splitting, if you introduce a higher and higher power of a Dane twist, for example, that's one way, would give you a family of splittings where the injectivity radius, so those do not have this R-bounded combinatorics condition, and the injectivity radius would tend to 0 in that family. So that can be realized by Dane, and the Heegaard genus is staying bounded. Because in fact, it's just, in the 1N case, you're not, you know, the surface is still homotopic across the Dane filling.
Any other questions? Well, I actually have a quick question, which is, what do you reckon, I mean, how important is bounded combinatorics to the creation of a model? I mean, would you
I mean, it shouldn't be, certainly not a necessary condition. I mean, that we're sort of hard at work.
Okay.
But it's just technical. I mean, there's certain things that are difficult to make go easily, and one of them is that this inductive process can sort of divide up in various ways, and when you have thin parts, you sort of can lose track of where you are and what you hope is your exhaustion of this handle body. And then another is getting a handle on what the minimal surface, as we've seen here, is doing in the presence of short geodesics, right?
Okay, right. Well, before we thank Jeff again for his very nice talk, we should also thank the organisers. So Jeff also happens to be an organiser, and Martin and Misha and Harold. It's been a great conference. It's really been a really good idea to get the two different camps together, and I think it's been very productive. I've definitely learned a lot. So thank you to all of you. Thank you very much indeed.
Amen.